As promised, now I'll work through the limiting reagent problem that I wrote in a separate video. If you haven't tried this problem yourself, I would recommend go look at the other video that set this problem up, try and solve the problem, and then come and watch this to see how you did. If you just watch me work through it without trying it yourself, that defeats the purpose. We have 75 grams of methane, 25 grams of oxygen, and we want to know how many grams of water will this reaction produce. You're told that the reaction only proceeds with 89.4% yield, so it's not 100%. We're given two reactants, so for this particular stoichiometry problem, we're going to have to do two separate calculations. One of them will be wrong. What we're going to indirectly do is determine which one of these two reactants is the limiting reagent. It's either the methane or the oxygen. There are several ways to approach this problem. What I like to do is I'll just start with what I'm given. In this case, 75 grams of methane. And I will calculate how many grams of water that should produce, ignoring the oxygen. Okay. We have grams of methane. We must convert to moles of methane to use a balanced chemical equation. So I've got the molar masses already written out. 16.04 grams of methane is equivalent to 1 mole of methane. Didn't bring a different color chalk. Grams of methane cancel. Now I have moles of methane. 1 to 2. We have a 1 to 2 molar ratio from our balanced chemical equation. And I already gave you the equation balanced before we started. 1 mole of methane is equivalent to 2 moles of water. I'm trying to write small so I can keep this on the board. Moles of, 1 mole. I'm trying to write too small. Moles of methane cancel. Now we have moles of water. 1 mole of water, the molar mass is 18.01 grams of water. Moles of water cancel. Normally we would be finished. However, our yield, 89.4%. If I were to solve the problem right now, that would be for 100% yield. So the last conversion factor, squeeze in right here, is yield. And the way we do that, we assume if we had 100 grams of water, theoretically, and this can have an infinite number of significant figures, put a dot there to give it 3, we would isolate 89.4 grams of water. Notice that this conversion factor, both of these have grams of water, so they cancel, leaving me in grams of water. Percent is a dimensionless unit. This is simply a way to set it up formally in my dimensional analysis table. If this was 100% yield, the reason we don't even bother putting it in is because this would be 100 divided by 100, which would just be unity 1, so we could ignore it. So I can put this into my calculator and get a number, but I'm not going to do that yet. And the reason why is we're going to have to do two problems. We've finished the setup for the methane. The next one is, what if we had 25 grams of oxygen? How many grams of water would that produce? Probably the most frustrating thing about trying to work through a problem like this is the realization that I have to do at least two calculations, possibly three if I had three reactants or more. Only one of them's right. So one of these calculations is going to be wrong, the other one's going to be right. No matter what you do, you will have to do at least two calculations for a problem like this. There are different ways to do it. This, I think, is the most straightforward. So 25 grams of oxygen, we want grams of water produced. Again, same idea. We need to convert from grams to moles. So 32 grams of oxygen is 1 mole of oxygen. Grams of oxygen cancel. We have a 2 to 2 molar ratio. So 2 moles of oxygen are equivalent to 2 moles of water in this equation. Now, from a mathematical point of view, you might say, well, 2 divided by 2 is 1. Why even bother with this step? It's not about the numbers. It's about changing the unit. Moles of oxygen cancel. Now we have moles of water. Doesn't matter what that numerical ratio is. We need this step to flip the units. So we have 2 moles of water, and we're trying to convert. And one of the things that you can notice, which will help speed things up as you're solving this, these last 2 steps are going to be identical. So 1 mole of water again is 18.01 grams of water, and our percent yield for every 100 grams of water isolated, we're only going to get, or I should say, for every 100 grams that we should isolate, the theoretical amount, we only isolate 89. Moles of water cancel, grams of water cancel, I'm left in grams, so we're done. By the way, I canceled this gram here, or I could have canceled this one, it's the same thing. So now, I have both of these setups. So you pick up your calculator and you start getting some numbers. Okay, so for the top reaction, when I take significant figures into account, I get 151 grams for the calculation with the methane. 3 significant figures, so that's why we're okay with that. The second one with 25 grams of water, 25 grams of oxygen, this gives me 12.6 grams of water based on the oxygen. 12.6 versus 151. So it's very obvious that we're going to run out of oxygen first. Oxygen is our limiting reagent. Therefore, 12.6 grams of water is the maximum amount of water we can produce in this reaction. Another way of thinking about it is, if we react 75 grams of methane with 25 grams of oxygen, we'll have some methane left over. We'll consume all of the oxygen. And in fact, if you want to, you can, now that we know this information, that the oxygen is the limiting reagent, we could actually work backwards and figure out how much methane is left over at the end of the reaction. So oxygen is our limiting reagent. I didn't specify that I wanted you to tell me that. However, to solve this problem, you must determine which one's the limiting reagent and then go from there. Notice this calculation and this calculation are completely separate. They're next to each other, but that's it. I don't combine them in any shape, form, or fashion because this physically does not mean anything in this context. We run out of oxygen, therefore 12.6 grams of water is the maximum we can produce.